All right, so we're in 6.1. We're going to do as much as we can in chapter 6. We're doing 6 tomorrow as well, and 8. Those are big days. Tomorrow will be a big day. 8's hard for people. All right, and then right away we have the exam right afterwards. Next, we have another exam next Wednesday. All right, let's get going. So, you ever seen that kind of thing before where they have the number with the exclamation point? What does that mean? It does. That's what I think too. It means 6, and you're like really excited about it, right? Now, what does it mean?
6 times 5 times 4 times 3 times 2.
Yeah, it's called factorial. It means go all the way down to 1. Exactly. You have a button on your calculator, probably. If not, you can just do it by hand. Yeah, it's called 6 factorial. Factor means things multiplied. Factorial, things multiplied all the way down. Whatever it is, 3120, 240, no, 360, is it 720? 720, okay. You might have a button. If you can find that button, great. It's an exclamation point somewhere. 8 factorial, something else big, whatever that is. 8. I'm getting 40,000. I got a button. 320. Getting that okay? If you really want the button, come up after class. I can show you where it is in your calculator. They're all a little different. Okay. And now it's saying compute, and then that's part A, part B. Now you might wonder why in the world we're doing such a weird thing. We'll get to the point in a minute. But right now it says compute the number of Hamilton circuits in K7. Well, turns out, what is K7? It stands for the complete graph, meaning all cities connect to all cities. Remember what we're doing? You probably don't even remember, maybe. It's all about, this is chapter 6, it's all about best way to visit a bunch of cities. Right, it's something that UPS would use, or FedEx, the best way to deliver packages, the most efficient way. That's the main thing we're trying to solve in this chapter. What's the most efficient way to visit a bunch of cities? And so first off, a complete graph is a graph where all cities connect to all cities, and 7 cities. A K7 would be, I don't know why we use K instead of C. I have no idea. K is not the first letter in complete, but whatever. Sounds for complete. So it means a map where all cities hit all cities. Do you know what I mean by that? So for example, hit it directly. So if you had, let's say city 1, city 2, city 3, city 4, city 5, city 6, and city 7. A bunch of cities, okay? And you're going to have a map where they connect to each other. Well, you could have, this would be a complete graph. City 1 goes to all the other cities. If it was missing, if there was no way to go directly to city 7, if there was no road from city 1 to city 7, for example, but there was from like city 4 to city 7, so you could still get to city 7 from 1, but not directly. You'd have to go through city 4, maybe, for example, right? Some areas, I guess, I'm sure in some more rural areas, there's not a direct road between every 2 places. That would not be complete. Does that make sense? If there's not a direct road between every 2 cities, between all the cities, then that's not complete. Complete means direct road from every city to every city. It's complete. It's as full as it can get. So if I was to draw a complete graph, so there would be city 1 going to all the other cities. Then I'd have to do city 2. He would go to all the other cities. Then I'd do city 3. He would go to all the other cities. Then I'd do city 4. He would go to all the other cities. Then city 5. Then city 6. That'd be a complete graph. That's a lot of roads. Wait, are they asking edges? Oh, circuits. I always get confused, sorry. Anyway, K7 means number of circuits. So yeah, so that is a complete map with 7 cities. That's still true. That's 7 cities. Every city has a direct road to all the other cities. And then they want to know, what are all the possible loops? Well, who knows? I mean, there's a lot of them, right? There's a lot of possible loops up there. I'm just going to give you the formula. Kn, let me write it somewhere. Kn, in fact, let me go to a fresh thing here. Kn, which again is complete graph, right? Every city hits every city within cities or points, right? The number of circuits is n minus 1 factorial. That's why we're studying factorial. Yeah, let me just leave it like that for now. So there's your formula. In fact, I could have just put this back over here, right? It's going to Kn equals n minus 1 factorial circuit. So if you have a complete graph where every city goes to every city, then you have n minus 1 factorial circuits. That's how many different circuits you have. That's how many different ways there are to make a loop. You know what a circuit is, right? It's a trip from every city to every city. So I could say, here's one trip. I'm going to start at city 3. I'm going to go to 1, then 6, then 4, then 7, then 5, then 2, then back to 3. That was a circuit. That was one circuit. That was one way to make a loop hitting all the cities. That's one circuit. And then there's a second one and a third one. And anyway, there's there's a bunch. There's a whole bunch. Do you realize that? Do you realize there's going to be a bunch of different ways to do that? Is that true? No. I'm trying to think if I could figure it out by hand. Because there's 7, then there'd be 6 choices times 5. Right. Right. From that one, start at city 1, there would be 6 factorial. Right. So K7. Yeah. Anyway, let's figure it out. So for K7, then it would be 7 minus 1 factorial, 6 factorial, which we just did. Isn't that the one, 720? 720 different circuits are possible. 720 different circuits are possible. Does that make sense? Do you know how they figure that out? Are you interested? How about I spend 1 minute? Because you're not going to be tested on it. But if you like logic. I took a whole class at Cal Poly about doing things like this. It was called counting. Doesn't that sound easy? It was called counting. It was a junior level math class. I was getting my math degree. It was a junior level, so, and it was titled counting. I thought, counting, right, that should be easy. That was one of the hardest classes I ever took, was counting. It was so hard. Teacher, well, let me show you. This is a counting problem. Like what? That's the kind of question they would put on the exam. They would say, so you have in points, in cities, same thing. How many? How many? Okay, so we can't do it. How many different loops, circuits, whatever you want to call them? How many different loops? That of course, the answer is n minus 1 factorial. We just saw it. But how did they come up with that formula? How do you know? How do you know how many different loops there are? Right? You know what I mean? Let's start with 4 cities. I got to go quick here. I'm getting all theoretical. I'm going to spend too long. Quick. I'll go quick. So say you had 4 cities. How many different loops are possible? This is the way you think in that thing. You go, well, you can start at 1, go to 2, 4, 3, back. That's one loop, right? Or, let's do it again. You could start at 1 to go this way and back. That's a loop. And then you could do lots of other things. You can go this way first, then this way, then there, then there. Oh no, you can't remember. You can't close the loop prematurely. You know what I mean? You can only return home once, then you're done, right? So I could say, I could do something different, right? So anyway, let me just tell you what you would do. Basically, if you were to write out a loop, write it in numbers, like 1, 2, 3, 4, back to 1. That's a loop, isn't it? Let's start at city 1, start at city 1, go to 2, 3, 4, back to 1. That's a way I could notate a loop. That's one loop. That's one circuit, isn't it? Or you could start at city 1, go to 2, then 4, then 3, then back to 1. That's a different loop, isn't it? Everybody see that? Am I making any sense at all? Right? Or you could, and then on and on. So basically, all the ways you could write 5 numbers in a row connecting all the cities is going to be a loop, isn't it? So that when they ask how many different loops are there with 4 cities, it's all the ways you can take the numbers 1, 2, 3, 4 and mix them up. All those ways are a loop, aren't they? So how many ways are there to do that? Well, think about it for a second. If you're going to start with 1, how many choices do you have for your next city? Right? Options, I call them. You're going to start at city 1, and then you got 3 options for your next city. You go to 2, 3, or 4. Right? You go to 2, 3, or 4. Let's say I chose city 2, went 1, then 2. Okay? Now how many options do I have for my next city? 2 options. If I went to 2, I could go to now 3 or 4. 2 options, right? Say I went to city 3. I went 1, 2, 3. Then how many options do I have for my next city? 1. Only 1. You got to go to city 4. But then you got to go home. How many options do you have for going home? Well, 1. You got to go home. There's not, I'm going to go home or home. No, it's home. It's one place, right? So, and then do you know that you multiply these? Does that feel right to you? Right? Like if I said I got 2 shirts and 3 pants, how many outfits? 2 times 3, 6. 6 different combos, right? So if you have options for decisions, you'd multiply those together. That makes sense? Now, would this be all the options for all the loops? Well, careful. It seems right at first time. It's a subtle field. Subtle. This field was so tricky, this class called counting, that the teacher, Dr. Hood, I had him for probably had him for 6 classes at Cal Poly throughout my bachelor's and my master's there. He was a hilarious guy. He was getting close to retirement back 20 years ago when I was a student, 25 years ago. Anyway, and he always thought we were so dumb. He always just, you guys, he'd always act like we were the stupidest. And he gave us the final. He gave us the final ahead of time, handed it to us. Said, here you go in this counting class. 20 questions. He said, the final will be 10 of them. Like exactly. I'm not going to change them at all. Half of them. 10 of them will be the final. 20 questions on a paper. Solve them all. You got a week. Next week, final will be 10 of them. Didn't help. I mean, I guess it helped a little. They were hard. They were really hard. Hard. Right? I mean, I did what I could. I didn't get an A in that class. I thought it was hard. And Hood, he would always act like, oh, you guys are so dumb. It was funny. Anyway, so think with me. The thoughts are subtle. Is that all the options for 4 cities? Is that it? Did we cover it? Right? Start at city 1. Then you have 3 options. Then 2 options. Then 1 option. Then you got to go home. Multiply that together. Whatever. That's 6, huh? 3 times, 1 times 3 is 3, times 2 is 6, times 1 is 6. 6? There are only 6 options? Well, somebody might say, wait a minute. You started at city 1. You could start at city 2. You could start at city 3, and you could start at city 4. And do that whole thing. Don't forget that. See, it's subtle. Don't think starting at city 1 counts all the loops. You're trying to count all the loops? All the loops don't start at city 1. Right? That's just all the loops starting at city 1. Right? How about the loops that start at city 2 or 3 or 4? So we got to multiply that by 4. There's going to be 4 times as many of these, right? No. Think a more careful thought. What's a loop? A loop's a loop. A loop's a circle. You could start anywhere. It's the same circle. All right, so I won't go on and on. You see how this field is subtle? You got to think careful about what things are and what things are different. So yes, this is all of them, it turns out. Because every loop starting at city 1 is every loop. Right? Did you understand that? Pick a loop. Start at city 3. 2, 1, 1, 4. Back to 3, right? That's a loop. You could start that same loop at 1. 4, 3 to 2. That's the same loop. A loop's a circle. It doesn't matter where you start in the circle. It's the same loop, right? That makes sense? We're going to actually need that thought today. And some other stuff we're doing. So that's not just a side. That's a main course of what we're doing today. Let me talk about that again to make sure you really got that. If I have 4 cities, you got to really get this. If I have 4 cities, 1, 2, 3, 4, 1, 2, 3, 4, and I say I'm going to do a loop. Here it is. I'm going to go 1, 2, 3, 4, back to 1, 2, 3, 4, back to 1. That's a loop, right? A trip covering all the cities coming back home. A circle, right? Is that any different than saying I'm going to start at city 2? Right, here we go. I'll start at city 2. And then I'm going to go to 3, to 4 to 1, and then back to 2. 2 to 3 to 4 to 1, back to. Is that a different loop? No, that's the same loop, right? Look at the picture. Does it look different? It's the same loop. So you see, these are the same loop. They're just starting at a different point in the loop. So we would not count that as a different trip. If you're UPS or FedEx and you're delivering the packages, that's the same trip. All the same roads, all the same cost. It's going to be equal cost, right? You're trying to find the trip, the loops, the circle that's the cheapest way to get to all the cities and deliver all the packages. That's the same trip, just starting somewhere else in the circle. You with me on that? So that's not different. So the answer is, it doesn't matter. If you count all the loops starting at city 1, you've counted all the loops, because the other loops are just starting somewhere else. So it's true. There are 6, which is what? For 4 cities, it's supposed to be n minus 1 factorial. So it should be 3 minus 1 factorial. Oh, sorry, 4. 4 minus 1 factorial, which is 3 factorial, which is 3 times 2 times 1, which indeed is 6. It's working. Do you see that? Am I losing you completely? Do you like the logic? Does that make sense? So what if you have like 10 cities? What if you have 10 cities? What are all the loops? Well, start at city 1, right? Because we said it doesn't matter where you start. Then, how many options for the next city you go to? If you have 10 cities total, you're starting at city 1. 9 options, then 8 options, then 7 options. You get it. See, 10 cities, you start at what? 1 lower factorial, huh? That's why for n cities, there's n minus 1 factorial multiplied together. Different loops, aren't there? There it is. That's the logic that leads to that formula. So, all right, enough said. So if we have n cities, then we have n minus 1 factorial different ways of visiting all the cities. Different loops, or they're formally called circuits. Hamilton, they're actually called Hamilton circuits, meaning, remember what Hamilton, probably you don't. Hamilton just means a loop where you hit them all and only once, right? Which is, why would FedEx want to go to the same city twice, right? It's just the most efficient way, hit every city once and hit them all. So n minus 1 factorial, okay. Estimate in years how long it would take the supercomputer to generate all the Hamilton circuits in K24. See, that stuff was hard, wasn't it? I took Dr. Hood. Dr. Hood, I remember one of these upper division classes, and that was just junior level. I took him for a higher class than that, and I got the lowest grade I ever got on an exam. Is that true? I think so. Yeah, I got that exam back. We took this one test in his class. This is a different class about a year later. 5 questions. 5 questions. We had 1 hour? We had 1 hour. 5 questions. I was able to finish. You're probably thinking, 5 questions. That's great. I was able to finish 2 in the hour, maybe 2.5, two and a part, I think. And I was working straight on. I wasn't, I was just going. They're proofs. They're big, long, couple pages each. Proofs is what they are. And I finished. Time's up. Hood's like, pass them in, guys. I'm like, shoot, we got like 2.5 problems. That's not good. And turned in my test. And got it back the next meeting, I think. And he's passing them back. I get it back. 42%. I think it was like 42. Of course, what I expect. I didn't get like half the test done, 42. I'm like, shoot, 42. I'm not really used to getting 42s, I look at my friend Mike was next to me. There's only like 10 people in the class. It was small. It was upper division, proving calculus kind of class. And he got his back, and he usually got A's on everything. He got like 45. I'm like, shoot, Mike, And then Dr. Hood, so he's so funny. He's kind of like half bent over at that point. He was always like, you guys, we had our written exams, but we had like the special exams to get into the master's program that were coming up, and we were all kind of studying hard. They give those, anyway, long story short, they give you really hard exams once every 3 months, and you got to pass them or you're out. It's really pressureful. He's like, you guys are coming up on your written. I tried to give you an easy test to make you comfortable as you're coming up on your written exams, but you guys did terrible. I remember he bent over, he goes to the board. The A's start at 40. I went, I got an A. Mike and I give each other high fives. I got an A of 40. So anyway, that was Dr. Hood. That was a taste of Cal Poly mathematics. All right. Anyway, estimate how long it would take the supercomputer to generate all the Hamilton circuits in K24. So, what are we talking about? So K24, what does that mean again? That's a complete graph. I don't know why we use K instead of C, whatever. Complete graph, meaning, all the cities, directly hit all the cities. Complete graph, 24 cities, right? So what are the number of circuits that are possible? What are the number of loops that are possible? What's the formula we just learned? N minus 1 factorial, right? That's going to be 24 minus 1 factorial, meaning 23 factorial. You guys have it? Got a calculator? You're going to need a big one. 23 factorial. Boom, I just got it. I got 23 factorial coming out to be 2.58, 1674. E, mine says E22. You might have a little different notation at the end. What's that mean?
Times 10 to the 22nd.
Yeah, that's scientific notation. Do you know that E22 thing? Yours might have a times 10 thing. Depends on the calculator how they display it. That means scientific notation times 10 to the 22nd power. What does that mean? What does it mean about real life numbers, Anybody know? E22? Times 10. So what if they wrote times 10 to the 22nd? What would that mean?
You move the decimal.
Very good. That means the decimal's not really here. It's really 22 places to the right. If that was a negative 22, it would be 22 places left. So when they go times 10 to the 22nd or E22, however your calculator displays it, it means the decimal's not really here. It's really 22 places to the right because it's a positive 22. Negative, it would be left. Okay, so what does that mean? Okay, well, move your decimal 22 places. Okay, here we go. Bless you. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 places. I got a lot more to go. Now, I don't know what the digits are after this. I'm just going to guess at zeros. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. There's the decimal. That's a big number. That's a crazy big number. That makes the national debt look like just nothing. Do you realize how big that number is? That's like crazy, crazy, crazy big. That's like there's 3 zeros, there's 3 zeros, there's 3 zeros, there's 3 zeros, there's 3 digits, there's 3 digits, there's 3 digits, and there goes the screen. It overwhelmed the screen. So there's that number. I don't even know what that is. 25, whatever. It's something crazy. Come on. Something really, 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 really. And I don't really know those are zeros at the back. I don't know what those digits are. I'll just fill in zeros to have something there. So, right, because here would be, you realize this right here is the millions. This is the billions. This zone, that's billions, whatever, if you had numbers there. This is trillions, so that's 20, there's the 74 trillion at the end of my numbers, 740 trillion. So this is, what's above trillion? Quadrillion, yeah, quadrillion. This is quintillion, so I guess we can almost get there. How do you say the 6? Sestillion? I don't know, whatever it is. So it's crazy big, crazy, crazy, crazy big. You guys know whenever you go through more spots, it's 1,000 of those, right? So, right, do you know a billion is 1,000 millions? Do you know that kind of thing? A billion's 1,000 millions. 1,000 billions is a trillion. So 1,000 trillions is this. So this is 1,000. This is a million of those, and this is so it's what is it? It's 25,000 million trillions. It's crazy. Crazy. It's more than the number of atoms in the universe. It's crazy. Okay, what's the point in all that? What is that? That's the number of different ways you can make loops when you have 25 cities all directly connected. Complete map of 25 cities. That means those are all the different ways you can have loops among 24 cities. There's that many different ways of doing loops among 24 cities. That's a lot of different loops. Okay, who cares? Well, this is a problem for UPS, FedEx, and anybody else in the real world that wants to solve these questions, that even wants computers to do them. That's always the answer these days, right? Computers can do it. We don't need math anymore. Computers will do it. They'll just do everything. Well, here we will see the weakness of technology and the strength of logic. Technology can't handle it. Let's see it. What if you had a supercomputer, right? You could rent some of the fastest computer in the world. Let's say a supercomputer can do, what is it? Well, you can see the answer right there. Let's say it takes, how fast can it, oh, there it is. 1 trillion Hamilton circuits per second. Let's suppose the supercomputer can examine and try to pick, because you want the computer to look at all the possible circuits and pick the cheapest route. Everybody understand the game plan in this chapter? We're trying to say, hey, FedEx, what's the cheapest way for you to deliver your packages to those 24 cities? How should the plane fly? How should the whatever go to save money in the most efficient way? How should you plan your trip to those 24 cities, or the mailman or the garbage man or the whatever? Anybody that visits a bunch of locations, businesses want to do this cheaply. This is big bucks to them. So, well, if you're going to find the cheapest way, you got to look at all the possible loops, right? How many loops are there? Oh, there's crazy amount of loops. Well, we got supercomputers. They can just go, brrr, just do millions and billions. In fact, let's even say they can do 1 trillion circuits a second. 1001, 1002, 1003. See, 3 trillion circuits were examined trying to find the best one, right? Even at that high speed, it would take the supercomputer 820 years to examine all these circuits and give you the best one. That's what it would take. How did I come up with that number? I'm going to show you the calculation now. Are we ready? You guys have your calculator? So let's do that. So, how to come up with that? Because you're going to have to come up with that. So, K24 again is 23 factorial, right? Take 1 away. We got that gigantic number, whatever it was, on your calculator. Take that then, and here's what you do to find out. That's how many total circuits, right? 23 factorial. You divide by a trillion. How do you divide by a trillion? Well, a trillion has 9 zeros. That's trillion, 1 trillion. Because it can do 1 trillion circuits every second. So you divide by a trillion circuits, that's how many seconds it takes now. Now, I don't know if you can put that into your calculator, depends on your calculator. If you can't, I'll say, or just do 10 to the power of 9. Because that's, right, got 9 zeros. It's the same thing as 10 to the 9th. Does that help? So guys, have your calculator with you? I want to help you with that. You should be bringing your calculator to class so you can, because I'm going to be helping, especially today. And I'll show you how to do it. Bring it next time. If you didn't bring it today, bring it tomorrow. And I'll be glad to show you how to do that on your calculator so you can get your homework done. 10 to the 9th power. It's an up arrow or it's like an X to the Y button. Depending on, some calculators have X to the Y. Some have an up arrow for their power. Is that making sense? Am I kind of blabbering on and not making any sense here? So you can do 1 trillion. If your calculator can take all the big enough screen for all those zeros, just do it that way. If not, do 10 to the power of 9 or 10 to the up arrow 9, depending on how your power button works. I'll be glad to come around and help you. And then divide by 60 seconds in every minute, 60 minutes in every hour, 24 hours in every day, 365 days in a year. And then you'll get that answer, 820. It'll round to about 820. Let me make sure it does on mine too. No, I got 819. I got 819,000. Oh, that's only a billion, isn't it? Oh, I blew it. There's 3 more zeros. Sorry, guys. Yep, that's only a billion. It's 10 to the 12th. Sorry. 12 zeros. There should be 12 zeros there. That's a trillion. So, yeah, 819.7 rounds to 820. I got that on my calculator just now. 820 years. That's how many years it would take the supercomputer. Are you getting that okay? Let me give you a minute to do that. Not making sense? That's probably worth me. Part B says the same thing for K25. So you would just, it's the same thing. You would just start with 24 factorial, right? Because you always go 1 down. The formula is n minus 1 factorial, right? So for 25, for K25, you would go 24 factorial. The rest is the same. Now, if they give you 1 billion, because I noticed I was going around, some people, they say 1 billion circuits per second instead of a trillion. you need to know a billion is 10 to the, ninth. Trillion, which is what I just did, is 10 to the 12th. So depending on what your homework problem says, you need to divide by either 10 to the ninth for billion or 10 to the 12th for trillion. But then you always have to do the 60, 60, 24, 365, because that's converting from seconds to years. Is that good? So the moral of the story is, why are we doing all this? The moral, why does the program, the computer, have us do this? The fact is, this isn't going to work. 820 years, I don't think FedEx is willing to wait, right? 820 years to give them the best way to deliver their packages this morning, right? It's not going to work. So we need a new game plan. Does everybody see the main idea here? We can't just look at every loop. Even having a supercomputer look at every possible loop and pick the best one is just not going to work. It's just too slow. All right, let's get this one done at least. All right, so optimal tour. So I'll come back to let's do basically let's start at A. Which one of those? Here we have 4 cities, A, B, C, D, and we have. Can you guys see that? Okay, let me make that. They want nearest neighbors, so ABC, yeah. So we have these 4 cities, and they want us to tell them the optimal tour. Like, what that means is the best way to travel from city A to B to C to D and back. So optimal tour and its cost, right? Yeah. Okay, I'm just going to make this bigger. Okay, so first off, so question A is optimal. Optimal tour. And optimal means best, huh? Like, what's the best way to, like, if you're UPS or FedEx and you got to deliver packages to all those cities and come home. Let's just start at A, make it easy. Let's just start here. Say the FedEx truck or the plane is in city A. It's going to have to visit all the other cities, but what order should it visit them in to be the most efficient, to cost the least in gas and employee time and airplane time and all that? So what's the best way? What do you think? From city A, wouldn't it be best to go this way to C, because 26, those numbers are how much it costs to go those different roads. So C, and then next go what? To D, I guess. B, yeah, B's a cheap road. B, but now you have to do the 48 to get, you got to go home. You got to bring the plane home. You got to go home. It's a loop. In the end, you got to go back to where you started, and then that means we have to take the high road, the most expensive road, the 48. We're forced to. So is that really the overall best loop? I don't know. This is kind of the problem we're going to have. We'll see how to resolve it. But for now, let's just say, I don't know, maybe. So A, what did we do? We did A, then C, then D, then B, then back to A. How much did that cost us? How much was A to C? 26, right? A to C was 26, and then C to D was 30, and then D to B was nice and cheap, 28. But then the bad one was B back to A, 48. Add those up. I don't know what that is. 132, thank you. 132. That's the cost of that road. So let's go back. They're basically asking us, they're asking us which one's best. So they're saying, is it A, C, B, D, A? Is that what we did? What did we do? A, C, D, B, A. A, C, A, C. Yeah, there's ours, B. We thought B was best. A, C, D, B, A, didn't we? That's what we just did. See? A, C, D, B, A. Is that really better than A, C, B, D, A? I don't know. You can just try it. Just add them up and you'll see. I'll try it. A, C, B, D, A. Just try that one also. So A, C, B, D, A. So let's try A, C, B, D, A. So if you start at A, go to C first. That's what, 26. A, C. Then to B, 46. And then to D, 28. And then back to A, 31. I don't think that's cheaper, is it? It is, yeah. Oh, what is it? 131? It beats it by 1? Okay. I guess that's a little better. So that's a little better. And then, well, maybe there's another one even better. What about the A, B, C, D, A? Is that better? Let's try that one. A, B, C, D, A. So you start at A, go to B. No, that can't be better. 48 takes the worst road. A, B, C, 46, D, 30, and then back to A, 31. Kind of getting scribbly here. 30, this is 30 and 31. Somebody got those added up? I don't think it's going to be better. 135, right? I'm sort of guessing.
155.
What is it?
155.
Yeah, I just knew it ended with a 5. That's all I knew. All right. Yeah, so that's not best. So the best road, I guess, is this one. I just tried them out. That's not very scientific. We'll have some better methods tomorrow. But so A, C, B, D, A is the best one. So the answer then is A, C, B, D, A. We just kind of trial and errored it. Does that make sense on that? Now, part B is going to say, do the nearest neighbor starting with A, do the nearest neighbor starting with B, and do the nearest neighbor starting with C. What is that talking about? So now, let me paste this here again. Okay, now we're gonna finally get into what these actual methods are. Here's the first of our methods. It's called the nearest neighbor. So remember what the goal of this chapter is. What's the cheapest way to make a loop, right? So you're the FedEx driver. You're starting in city A, and you're saying, what's the cheapest way to visit all the cities? Well, I don't know. Let's just try something. The nearest neighbor method is the first way of trying. The stress is on trying. It does not guarantee the best answer, but trying to find the best answer. Just start at A and go to your nearest neighbor every time. So who's my nearest neighbor? Who's closest? Who's the cheapest trip from A? If I go D, that's 31. C is 26. B is 48. So who's closest? Who's cheapest? The 26 to C. Right, that's pretty much what we did last time, huh? A to C is 26. And then who's my next from C? You can go to D for 30 or B for 46. So I'm going to go to D, huh? This is what we did a minute ago. I'm going to go to D, and that cost me 30. And then from there, you have no choice, huh? There's only one city left you haven't visited, and you have to go home. So remember that when you're down to just one city, don't worry about numbers or anything. You've got to go to that city and you got to go to home, no matter what it costs. So 28 to go to B, and then you got to go home, which is the 48. That's why this doesn't end up being the best method, huh? And add that up. What was that again? 132? But that is the answer that nearest neighbor method gives you. It's not the best answer, as we've already seen. But it is the method of just always driving to your nearest next city. Turns out that's not the overall best way to make a loop. There's a way a little bit better we saw already, but that's pretty good. You know, it's better than nothing. Is that okay there? Let's try now. Part C says, do it again, nearest neighbor, but this time, nearest neighbor, start at B. They say, do the nearest neighbor thing, but start at city B. So start here at B. Let me let you do it on your own papers there. So start at city B, make a loop, end up coming back to B in the end. Visit every city, and every time go to your nearest neighbor. So what would that be? Start at city B. Who's the cheapest road from B? I could go to A for 48, or D for 28, or C for 46. So clearly I'm going to go to D for 28. And then from D, now I'm here. What's the cheapest road from here? Going to be C for 30. And then once you are at C, you've only got one city left, huh? So there's no choice. You have to go to that city, and you have to go home. So you go to that city, it's 26. Then you got to go home. In this case, B is home, which is 48. Add that up. That's 132 again, isn't it? That's really the same exact loop, I think, just starting at a different point. See how those are exactly the same loop? They're just starting the circle in a different spot. It's not really a different trip. And then finally, part D part D says do the NN, nearest neighbor, start at C, I believe. Isn't that what they say? Yeah, start at A, B, and C. So start at C. Can you do nearest neighbor now starting at C? So start at city C. Go to your nearest neighbor. So C. Who's my nearest neighbor from C? Be A for 26. And then from A, be what? I guess the D for 31. Okay, I'm here now, right? And at this point, there's only one city left I haven't been to. So I have no choice. I got to go to city B for 28, and I got to go home. Home is back to C for 46. So add those up, 15. Is that 131? Anybody got that? I know it ends with a 1, so I'm guessing at the rest. 57, 77, 85, 131. Yeah, 131. So that's actually a little bit different loop, isn't it? And a better loop, huh? That's actually a better loop. That's actually the best answer that we found, by guessing around earlier. And by the way, you could rewrite that answer starting at A, couldn't you? Do you know what I mean? Because that's what they'll ask you to do on the test. Let me go back and see if they did that. Yeah, oh, they do that here too. They probably did that here too. I don't know. Yeah, so this is the answer, the loop, nearest neighbor starting at C, but you could rewrite that. Let me do it right here. Can you see it down there? Yeah. Let me rewrite it. Starting at A, because a lot of times they'll on the multiple choice answers on the next exam, next week, all the answers will be starting at A. That doesn't mean they originally found it starting by A. They might have started at C or B or something, but they rewrote it's a loop, so you can rewrite it starting anywhere in the loop, right? So rewrite it starting at A, so it'd be A, D, B, C, and then back to A. That's the same loop, isn't it? Same loop. And also you could go the other way. You go A, C. You go backwards. A, C, B, D, A. Same loop, forward or backwards. And it'll be the same cost because it's all the same roads, isn't it? It's the exact same loop, just written in with different starting point. Does that make sense? That way of doing it, we're going to have 3 ways. We're going to have nearest neighbor, repetitive nearest neighbor, and something called cheapest link tomorrow. We'll get those other ways of doing it. That's just the first of the 3 different ways of trying to find the cheapest way to visit all the cities. All right, well, we are at time. Let me